Hi, this is Brian Birdwell, and welcome to Session 8. Today we're going to talk about number properties. Number properties can be the thorn in the side of many folks taking the GRE because they test difficult subjects like prime numbers or exponents, square roots, negative fractions, raised to exponents, things like this. Things that just kind of make your brain hurt at first when you look at them, especially if you haven't looked at this kind of math in a long time. However, this problem group does present us with at least two opportunities. One of those is if we know the rules and we are familiar with how they work, and there's a less than infinite variety of them, I assure you. There's only so many different flavors of these. And if we're familiar with that, we can actually save a lot of time on these problems and work them quite quickly. The other good thing about this group of problems is that typically, if you don't know the rules, there will be sort of a hard way to do the problem, so to speak. You can plug in numbers, test numbers, and do a lot of sort of hard work and still arrive at a solution. So they offer us both those opportunities, the opportunities to learn the rules, be quick and efficient, and also the opportunity to hone our skills choosing numbers and doing things the hard way. So let's go ahead and get started. I'll give you 2 minutes for this first one. All right, now the most important phrase in this problem, of course, is must be. We are to find the numbers that we know n is divisible by. And we know that it's divisible by these two numbers, 4 and 21. Now, as is hinted by the title of this slide, divisibility is really a function of prime numbers. And this can be kind of difficult for a lot of students to wrap their head around. I invite you to think of it as if prime numbers are the ingredients that make up other numbers. So every number can be broken down into multiples of prime numbers. And every factor of a given number is just a combination of its prime factors. So think of 12 for a moment. 12 has factors. Of course, 1 and 12 are factors. Those are always factors of any number, 1 in itself. And then the other factors of 12 are 2, 3, 4, and 6. And as you'll notice, 4 and 6 are not prime numbers, but they are combinations of 2 and 3. So it so happens that if you break 12 down into its prime factors, you'll find 2 2s and a 3. And with those ingredients, those like the atoms, so to speak, that make up the number 12, you can create all of its factors. So with the 2 2s and a 3, you can create a 12, you can create a 4, and you can create a 6. So with that in mind, looking at these problems, anytime you see the word divisibility, you're most likely going to have to utilize primes in some form or fashion. So what we know here is that n has 4 and 21. So what this actually means is that n has 2 2s in it, and it has a 3 and a 7 in it. So at the bare minimum, what we know about n is that it has every number on the list. So 2, 3, and 7 must be included there. So we've got one of our answers already. And any multiple of these numbers as well. So we can look at the list here and see which ones we can make, or we can make all of our combinations and then proceed to the list. Either way. Can we make an 8? No. We need one more 2 if we're going to make an 8. We only have 2 2s, and we need 3 2s in order to build an 8. 2 times 2 times 2. Can we build a 12? 2 times 2 is 4, and 4 times 3 would give us 12. Absolutely, we can build a 12 with these ingredients. Can we build a 14 with these ingredients? Well, we have a 2 and we have a 7. Absolutely. 2 times 7 is 14. We can definitely build a 14. What about a 24? Well, we have a 2, and a 3. The most that will give us is 12. 7 doesn't go into 24. We cannot build a 24. What about a 63? Well, we have a 21. We have a 21 times 2, which would give us 42. And then we have another 2, which would give us 84. So we never can build a 63 with these ingredients. These are our 3 answers: 2, 12, and 14. All right, just 75 seconds for this quantitative comparison. And I encourage you to try to go even faster. So the surest fire way to do this problem is just to bust out factor trees and compare them to one another. So let's build a factor tree for 126. If we do so, and I usually just start with the easiest way to break it down. You might see other combinations or other ways to get there, and that's totally fine. Myself, I usually just start, if it's an even number, dividing it by 2, unless there's an immediate recognition of a bigger, easier number that would go into it. So 2 and 63. 63 breaks down into 9 and 7. 7 is prime, and 9 breaks down into 3 and 3. So for the number 126, the biggest prime factor is 7. For the number 128, we can break it down into 2 times 64. 64 is 8 squared, and each 8 is a 2 cubed. So in fact, 128 has only 2's as its prime factor because 128 is 2 to the 7th power. Therefore, our answer here is A. Column A is larger. Now, one thing you might recognize is there's sort of a Jedi shortcut to this problem, and that is if you are to the point with your GRE studies where you've memorized all the necessary equations and you're really pushing for a top tippity top score, then it can be a good idea to memorize some powers of 2, some powers of 3, some powers of 4, and some powers of 5. And with 2, you might have immediately recognized that 128 is 2 to the 7th. Therefore, if the number 126 has anything in it other than a 2, it's going to have a bigger prime factor in it than 128. So you might be able to recognize that very quickly and immediately recognize that 126 has a 3 in it, for example. Therefore, the answer would automatically be A. For the rest of us mere mortals who don't automatically recognize that 128 is 2 to the 7th, factor tree is a surefire way to go. Okay, I'd like you to work these two problems together. I'll give you the full 2.5 this time round, but challenge yourself to do these quantitative comparisons a little faster because every 15 seconds that you can save on a given quantitative comparison problem is another 15 seconds you have to invest on one of those really difficult data interpretation problems down the line. Ready, go. The easiest way to get tripped up on least common multiple and greatest common factor problems is just to get confused about which one is which. So take your time and parse it out if you have any difficulty there. Least common multiple, it can be misleading because of the word least, when in fact it's always going to be a number bigger than those two numbers. Whereas with greatest common factor, it's going to be a number smaller, even though the word greatest is there. So least common multiple of 12 and 16, I think the most straightforward way to do a problem like this is actually just to start listing them out. So what are the multiples of 12? We've got 12, 24, 36, 48, 60, 72. Stop whenever you feel like it once you got 4 or 5 up there. And with 16, we've got 16, 32, and 48. So there we go. 48 is the least common multiple of 12 and 16. Now, with greatest common factor, we've got to do a little different work. We've got to start dividing these numbers up into their factors and not their prime factors. There's a big difference between prime factors and factors. Factors are just all the numbers that will go into these two. And what's interesting, of course, about the pair 48 and 96 is that the number 96 is actually 48 times 2. Of course, 48 is a factor of itself. 1 and 48 are the first factor pairs you might think of for the number 48. And 48 is also a factor of 96. Therefore, our answer for this one is C. These quantities are equal. The number is 48 for each of them. Now, for the second problem, greatest common factor of 18 and x is 9. So on our first attempt here, or our first sort of strategy for the problem, we might just think, okay, so both 18 and x are multiples of 9, but x can never also have a factor of 18. So we know x has to be at least 9, and then it could be any other multiple of 9 that doesn't include 18 as a factor. So we could kind of make a list, and we could check that list out. So x could be 9, because 9 clearly has a factor of 9. It cannot be 18. So the next multiple of 9 that's available is 27. It cannot be 36, because 36 has 2 18s in it. It could be 45. It can't be 54, because 54 has 3 18s in it. It can't be 63. And it can't be 72, because 72 also has 18 in it as well. And we could keep going, but by the time we get out, 6 or 7 examples like this, we should be able to see a pattern here. And what you may notice is that x can only be odd multiples of 9. And once you recognize that x can only be odd multiples of 9, you're almost all the way to the solution. So without even phrasing it that way, you could just turn to column A here, and you could say, well, what is the remainder when x is divided by 2? I don't even know what x is yet. What's the remainder when 9 is divided by 2? Well, the remainder is 1, for remainder 1. What about when 27 is divided by 2? 13, remainder 1. What about 45 divided by 2? 22, remainder 1. What about 63? 31, remainder 1. And so it turns out that the remainder is 1 every single time. And our answer for this one must also be C. One other way to attack this problem is based on the recognition of the factors, even the prime factors, of 18 and 9. So, for example, we could think about 18 as being composed of a 9 and a 2, or 2 3s and a 2, though it's really not necessary for us to break it down that far here. And x, we could think of, is going to be composed of at least a 9. In fact, that's the largest factor that can go into 9. Something else, we don't know how many other factors. I mean, the number x could be 9 billion for all we know, but we don't know what other factors are in there. And we know that it cannot have a 2. And this is a really important recognition, that x cannot have a 2, because if x has a 9 and a 2, then it's going to have a factor of 18. And that's not possible in this scenario, because the largest common factor needs to be 9. So what this tells us is that x has no 2's in it. And if x has no 2's in it, it must be odd. And anytime we divide an odd number by 2, we're always going to get a remainder of 1. So again, there's sort of the hard work, just making some examples and recognizing the pattern after the fact. And there's also the second method of sort of being astute with how these rules play out, looking at the various factors and narrowing in on what must be true about x. This is kind of the fun part of number properties. Okay, 2 more problems. And for this pair, I'm going to give you guys only 3 minutes, so a minute short of your 2-minute per problem average here. This is your opportunity to put some time in the bank to use on more difficult problems down the line. Now, the moment you see a number raised to x on the GRE, there is an incredible likelihood that your first priority is to reduce that number or that coefficient to its prime factor. And that's exactly what we should do here, because we'll notice that this is 2 to the 12th. 8 to the x, it's very difficult to work with these two numbers and learn anything about them. But of course, 8 can be broken down into powers of 2. So when we symbolize the left side as 2 to a certain power, and the right side is already 2 to a certain power, this makes it possible to actually compare them. So here what we can do, is simply symbolize it this way. We know that 8 is 2 to the third, and that this is also being raised to the x. So we have 2 to the 3x equals 2 to the 12th. And when we have like bases, the exponents must be equal in an equation like this. Therefore, we can just extrapolate that 3x equals 12, and therefore x equals 4. This problem, of course, taking advantage of the rule that when you raise an exponent to an exponent, so for example, if I have 2 to the third, symbolized as 8, raised to the x power, that those two exponents, the 3 and the x, are multiplied together. And just by knowledge of that one simple rule, this is money in the bank. This is the kind of problem also that makes me feel really smart on the GRE. What about you? For whatever reason, it's really satisfying because it looks like such a puzzle. And in fact, the solution is so simple. It's very satisfying to complete one of these. And the same is true of a more difficult version of the same problem as we see below. So again, just like the one above, you must immediately recognize that this number can be broken down into powers of 2, just like this number can be broken down into powers of 2, and the second number can be broken down into powers of 3. All we have to do is do that correctly and then make sure we answer the correct question, give them what they're asking for, and we're home free on a problem like this. So 32, of course, is simply symbolized as 2 to the 5th, and 27 is 3 cubed. So with this information, we know that 2 to the 5th needs to be raised to the 6th power, and we know that 3 to the 3rd needs to be raised to the 2nd power. When you raise an exponent to an exponent, you multiply. So this in turn gives us that x equals 5 times 6, which is 30, and y equals 3 times 2, which is 6, and x over y leaves us with a solution of 5. Pretty fun, huh? Let's try a few more. There are 3 problems here. Ordinarily, you would have 3 minutes and 45 seconds to do this. I'm going to challenge you to go a little faster, and I'm going to give you just 3 minutes to complete all 3 of these problems. Ready? Go. All right, if you need 45 extra seconds or you'd like to take that extra time, which would be the standard 75 seconds per question, go ahead and pause the recording and take that time now. Otherwise, let's go ahead and take a look at the first problem. This problem is very easy to misread. So for a moment, I want to direct you away from this problem and just to a short alternate example. If I were to tell you that 8 was equal to 2n, well, then you would know that n had to be 3. This is the only way the problem works. 2 to the third power is 8. However, if I were to tell you that 8 is divisible by 2n, then n doesn't have to be 3, because 8 isn't just divisible by 3. 8 is also divisible by 1, which would be 2 to the 0 power. 8 is divisible by 2, which would be 2 to the 1 power. 8 is divisible by 4, which would be 2 squared. So it's very important here that you don't read this problem as saying that 18 to the 4th is equal to 2 to the x times 3 to the y. It's virtually guaranteed that some of you have made this mistake. But having recognized it now, you'll clearly see that there's no way to answer this problem. Because y could be 0, y could be 1, x could be 0, x could be 1. They could be any number of a combination of factors or elements. Therefore, our answer here is D. The next problem looks a lot more intimidating, I think, than it actually is, and it does test one very important skill, and that is your ability to recognize when you can factor out a larger number from all three of the numbers in a polynomial. So when you have a series of subtraction or addition, you can always remove the largest possible factor from each element in the group. So what that would look like here is obviously 3 to the 13th and 3 to the 12th are too large, but I can take a 3 to the 11th out of each one of these. And if I do so, then I get a number that looks like this. 3 to the 11th times 1, which is 3 to the 11th factored out of itself, minus 3 to the 1st, which is the remaining 3 once I remove 3 to the 11th, and 3 squared, which is the remaining 2 3's once I take out 11 of the 3's from this particular number. Further reducing, that gives us 1 minus 3 plus 9, which gives us 3 to the 11th times 7, which in an interesting turn of events make these two otherwise completely different looking numbers absolutely 100% equal. And our answer here would be C. As far as guessing strategies go, this is not a very concrete example of a guessing strategy, but the fact of the matter is there will be problems on the test where we have to take a wild guess in all likelihood. On a problem where the numbers look so incredibly different, there's no 7 anywhere in quantity A or column A. Column B and column A look so different that we might think, you know what? The GRE wants me to think that these numbers are not equal because they look so completely different. Therefore, if I have absolutely no idea what to do on a problem like this, C is a good guess. Moving on to the problem on the bottom, it's kind of a simple test of our ability to manipulate inequalities and compare numbers raised to exponents. So the first thing to do, of course, is just simplify the inequality by rearranging things. Add the 1 and we get a negative 2. Divide by 2 and we get Q is bigger than negative 1. But we have to combine this with another really important fact here, and that is that Q is negative. So if Q is both negative and bigger than negative 1, this tells us that Q must in fact be a negative fraction. Now we need to consider two things. We have on our hands a negative fraction in column A, and in column B, we have a negative fraction raised to the third power. So this is the first thing to check, because if it was an even power, then we would have a positive number on our hands and we could answer B very easily. However, it's an odd power, so we have a negative number in column B as well. And then we have to think, what happens when we raise fractions to exponents? And the answer is they shrink. They get smaller and smaller and smaller and smaller. So since both columns are negative numbers and column B is getting smaller because it's a fraction being raised to an exponent, we know with confidence that column B is bigger. The first one here looks pretty rough when we first consider it. Wow, the square root of 2 to the 36th power. Some of you might be scratching your heads wondering how on earth to attack this problem. And if that's the case, what I invite you to do is turn your attention to column B for a moment instead, because it's so cozy. It's like a warm fire on a cold winter night compared to the number in column A. So how can I compare the number in column B to the number in column A without sort of dealing with the number in column A? Well, one thing that I could do is I could recognize that 64 was a power of 2. And I could start there. Okay, so 64 is definitely a power of 2. How many 2's are in 64? Let me count for a moment. There's 6. Okay, so 64 is 2 to the 6th. Now, if I was going to square that, you see I could square this number instead of getting the square root to compare to what's under this square root here. So I'm sort of shortcutting the problem by doing this. If I say, wow, okay, so 64 is 2 to the 6th, and 2 to the 6th squared is 2 to the 12th. Therefore, one way to represent the number 64 is to call it the square root of 2 to the 12th. And this is useful in a couple of different ways. For one thing, if I can recognize that 64 would be the square root of 2 to the 12th, I could see that, wow, the square root of 2 to the 36th is going to be a lot bigger than that. And I could already recognize that my answer would be A. Something else I could do is I could recognize that when I square root 2 to the 12th, I get 2 to the 6th. I just proved it to myself by squaring it first. And so what's interesting is kind of by reverse engineering If I didn't already know how to take the square root of an exponent, now I do. You just cut it in half. That's all you have to do. And this is a mathematic truth because, as it turns out, a square root is just simply raising something to the exponent 1/2. It's like shorthand for doing that operation. Therefore, column A could be written as 2 to the 36th to the 1/2 power, meaning that the number in column A is equal to 2 raised to the 18th power. So we have 2 to the 18th versus 2 to the 6th. A is clearly larger. So there are two ways of solving the problem. And again, I think there's two important takeaways here. One is that you cannot deal with this number at all and still be able to compare it to 64 to try to get a handle on whether it will be bigger or smaller by representing 64 as a power of 2, squaring it, and then representing it as the square root of itself squared, which you know has to be true. You know these have to be equal to one another. Another thing is that 2 to the 36th, well, it's just thinking about exponents. 2 to the 36th is a massive number, huge number. If 64 is 2 to the 6th, 2 to the 36th is an incredibly large number. So square rooting that in all likelihood is going to be much, much, much larger than 64. So A would be a really tactful, wild guess if you had nothing else to do, if you had no other clue on the problem, just by recognizing how large the number 2 to the 36th power must be. And now you know, if you square root a number raised to an exponent, just half the exponent. That's all you have to do. Okay, moving on to the second problem here. There's something really interesting here, I think, to recognize about working quantitative comparison problems. And that is that the fundamental question in a quantitative comparison problem is sort of, how are these two quantities related? Are they equal? Is one of them less than the other one? Is one of them greater than the other one? Etc. So what we sort of have here on the line is a kind of equation. But it's an equation that we're not sure if they're actually equal. So it's like we're asking ourselves, is this an equation? Are these guys equal or not? You know, what is their relationship? And what's interesting about this dynamic, is that it allows us to treat each column like the side of an equation, which means we can square both sides and still be doing the comparison we were originally asked to do. And so squaring a square root should be sort of your natural instinct anyway. The moment you see this, you want to get rid of it, just get it out of there. Now you have a means and a justification for doing so. You can get rid of this square root if you also square this side. And that way you're still asking yourself the same question. Are these quantities equal or not? And squaring them allows you to answer that question if you square both sides. You can do anything you want to both sides. Subtract 2 from both sides if you need to. Divide each side by 2 if you want to. They work just like an unspoken equation. So with column A, when we square it, it's fairly obvious. The square root disappears. We get x to the 4th plus y to the 4th. With column B, when we square it, it's very important that we don't rush through this. We do it the long way, and that we remember that when we square a polynomial that has addition or subtraction involved, we're going to get at least 3 elements. We're going to get, through the FOIL method, we're going to get some x's, in this case 4 of them, x squared times x squared. We're going to get some y's, in this case 4 of them, y squared times y squared. And we're also going to get this middle element, which is what always happens when we FOIL if it doesn't disappear. So x squared, y squared, and again, x squared, y squared for the outside and inside terms. So now we have basically the same quantity in column A represented here in column B, with the difference that column B has added this middle term. But don't go running to answer choice B yet, because we still have to answer one more question, and that is this positive or negative? Because if we're adding a negative number to the quantity, then the answer would be A. But if 2x squared y squared is positive, then the answer must be B. So let's take a moment to consider. Oh, they're both even exponents. So no matter what, whether x and y are negative numbers or not, this middle term is going to be positive. So column B is going to be bigger than column A by exactly this amount, 2x squared y squared. Now we can answer confidently answer choice B and move on. All right, 2 minutes for this one. First of all, recognition is very important on a problem like this. When the GRE gives you several variables related by an inequality sign, most of the time they're not interested in the actual values of those variables. They are interested in the signs of those variables. So first things first here, we should follow just good fundamentals and rephrase or work out the inequality before we proceed any further. So if we just take our basic inequality here and work it out, we'll find that the A's cancel out, and we move a B over, we can divide by 2, and we know that B is greater than 0, B is less than 0, 0 is greater than B, which gives us answer choice number 2 over here. And before you work too hard trying to figure out whether A is less than 0 or whether AB is less than 0, just remember that the A's canceled out. In the one piece of information we are given, in other words, the A's don't even exist. It looks like they do because they did it first, but this and this are absolutely identical. The bottom is the simplified version of what occurs at the top, therefore it's all we need. A doesn't even exist in this inequality, therefore we know nothing about A and we can confidently move forward. All right, here for a quantitative comparison speed round. Earlier, I knocked 45 seconds off a group of 3 and gave you 3 minutes to do the 3. Now I'm going to challenge you to go even faster, only 2.5 minutes to work these 3 problems. Ready? Go. The first one here I think is pretty fun. First things first, we need to recognize that since the number inside the parentheses is 1, I mean, I know it has a negative sign on it here, but it's essentially 1 raised to certain powers. That means that the number is going to be 1 or negative 1. So our only concern here is this number going to be positive or negative? We don't have to worry about the actual values of the exponents at all. So here, 2n. Well, n is an integer, great. Any integer multiplied by 2 is going to be even. A negative number raised to an even power will always be positive. Therefore, this half of column A is positive. With the next one, we're raising it to an odd power. A negative number raised to an odd power is going to be negative. A positive times a negative yields a negative number overall for column A. For column B, we have 2n, which is definitely going to be even, minus 3. Anytime you have an even number and you subtract 3, you are always going to have an odd solution. Negative number raised to an odd solution, negative number. Negative number raised to an odd exponent, negative number. So in column B, we have 2 negative numbers multiplied together, which will yield a positive. Therefore, column A is a negative number and column B is a positive number. Therefore, column B is our answer. And of course, that number is going to be 1. A is negative 1, B is positive 1. Hopefully you recognize that, and very quickly, because the time constraints were very real. With quantity A, excuse me, with number 2 here, all these numbers are equal. Okay, great. So xyz is the same as x to the third, is the same as y to the third, is z to the third. We have the absolute value, and that tips us off that, by the way, absolute value is always a dead giveaway that you're dealing with sign. So the moment you see the moment you see absolute value, you want to be considering, well, positives and negatives. And here, obviously, this number is going to be the same. The question is, are x, y, and z negative or positive? Because if they're all positive, then column A and column B are equal, in which case we would have to eliminate, sort of following good strategy here. We wouldn't just choose an answer, we'd eliminate in one case. So if they're positive, both columns are positive, which means that A will never be bigger and B will never be bigger. And in the next instance, we'll consider what if they are negative. So if they're negative, column A is going to have a negative solution since there's an odd number of elements involved. And since column B has absolute value, it's still going to be positive, meaning in that instance that they could never be equal, leaving us only with answer choice D. In the final instance, this is another classic GRE giveaway that they are testing your knowledge of signs. Anytime they give you a product of two variables in relation to 0 with an inequality, they are telling you something about the signs. Now take a moment and think. What do we know about the signs for A and B? Well, we don't know if they're positive, and we don't know if they're negative, because either one would give us a solution. If they're both positive, then that's correct. They're greater than 0. Or they could also both be negative. So what we know is not whether A and B are in fact positive or negative. What we know is that whatever they are the same. If A is positive, then so is B. If B is negative, then so is A. And likewise, with BC being less than 0, we don't know which one's positive and which one's negative. We simply know that one of them is positive and the other one is negative. So we can think of this as B and C having different signs. And now we just have to take 1 and add it to 2. If A and B are the same and B and C are different, this must mean that A and C are also different signs, meaning that quantity A is going to be negative. Therefore, quantity B, 0, is bigger. Our answer is B. I want to show you two approaches to this one. The first relies on the actual number properties method, just knowing the properties of odds and evens. Of course, we're looking for the number that can never be an even integer. And we can imagine there's three possibilities here. It could always be an even integer, it could sometimes be an even integer, or it could never be an even integer. And it's this third possibility that we're after. With answer choice A, anytime we have multiplication involving an even integer, we're always going to have an even integer. So this one is always even and it's out. With A over B, an even integer divided by odd. So you could think even divided by odd. Well, I could have 12 divided by 3. That would give me 4. Therefore, that's at least possible to be an even integer. Obviously, sometimes it could not be as well. If I had, for example, 14 divided by 3. Well, that's not even an integer at all. With B over A, odd divided by even, you could think 3 over 2, not an integer. 11 over 5, not an integer. 25 over 4, not an integer. And you would be correct. You can never divide an odd number by an even and arrive at an even solution. With the final two, an even number raised to any power in the whole world will always give you an even solution, and an even power raised to an odd power will always give you an even solution. An even number raised to any kind of power always yields an even result. So as you can see, we have three answer choices that always give us an even integer, one that just sometimes does, and then only one correct answer that never does. Now, if you didn't want to deal with the properties of odds and evens and you wanted to use the old reliable plug and chug method here, it's answer choice B that may cause you some problems. So let's see what that process may look like. If you tried A is 2 and B is 3, and by the way, 2 and 3 are my all-time favorite numbers for plugging in on the GRE. The vast majority of times that I need numbers to plug in, if 2 and 3 fit the rules of the problem, then I will use them anytime I can, and they'll arrive at a solution. In the event that they don't, we have to refine our numbers and try something else, as is always the case with plugging in any number. So what would happen here, of course, is that if you plugged in 2 for A and 3 for B, you'd get 6, 8, and 128 for A, D, and E. Those would drop out very quickly. You would get 2/3 for B and 3 over 2 for C. So you would eliminate A, D, and E, and you would have to further test B and C. And that's okay. Don't freak out if something like this happens when you're plugging in numbers. As you guys probably know by now, this is an indication that things are working. You just have to do it one more time, which is often the case with plugging in numbers. You don't always pick the best numbers for the job on your first try. So now you can see that division is the issue. So what you might do is try a bigger A. What if A was 6 and B was 3? Then B would be an even integer. C would be 3/6, and that's, again, our correct answer. By the way, as I just said, an even number to any positive power is going to be even, and an odd number, just so you know, to any power is always going to be odd. So given that x is an integer, we're looking for a number that must be even. So the moment the word even enters into the problem, we can already predict that odds and evens will be an important issue here. For the moment, let's restrict ourselves to positive integers just because that's easier to think about generally than negative integers. And let's cross out any obviously wrong answer choices and narrow our way down to the more difficult ones. So does answer choice A have to be even? Well, no, clearly it doesn't have to be even because x could be odd, in which case A would be odd, or x could be even, in which case A would be even. But since it could go both ways, we can safely eliminate answer choice A. B looks a little complicated, C looks complicated, D looks complicated. Let's take a look at answer choice E. If x is odd, then this is going to give us an even solution because it's going to be an odd plus an odd. You could think 3, for example. 3 times 3 would give you 9, plus 3 gives you 12. So it could be even. But what if x is even? 3 times 2 is 6, and an even plus an odd is always going to be an odd. 6 plus 3 is 9. So we could easily eliminate A and E, and now turn our attention to B, C, and D. And what are the possibilities for answer choice B? Let's ignore the x squared for just a moment and just focus on 2x plus 2. Regardless of whether x is even or odd, this number is going to be even, and 2, adding 2 to that number is going to keep it even. So we're going to be adding an even number to whatever x is. So if x is even, this whole number will be even. And if x is odd, this whole number will be odd. Therefore, it doesn't have to be even, and we can eliminate answer choice B. Moving on to answer choice C, a little different here with 5 and 6. So with 5, there's no telling. If x is even, say for example 2, then this is going to be an even number. But if x is odd, for example 3, then this is going to be an odd number, so it matters here. Let's consider the whole thing. If x is even, this would give us an even plus an even plus an even. That's going to give us an even number. If x is odd, this gives us an odd plus an odd plus an even. And what does an odd plus an odd always yield? Think 3 plus 3, 5 plus 5, 7 plus 7. Odd plus odd will always yield an even solution. Adding 6 to that will keep that solution even. So no matter what the circumstances are, answer choice C will always be even. Quickly looking at answer choice D, if x is even, 6x will be even. Adding 4 will keep it even. If x is odd, 6x will be even, 4 will be even, and we'll have even plus an odd, yielding an odd solution. And here are those ideas written up on the screen if you want to pause the recording here and just check out what I just said a little slowed down. These are the two options, if x is odd or if x is even. If x is odd or if x is even. Continuing on down the line. Note that this entire time we were really able just to ignore the square here, because squaring an even number keeps it even, squaring an odd number keeps it odd. So we could just, for all intents and purposes, totally ignore that square. You could plug in numbers here and still arrive safely at a solution as long as you plugged in both an even number and an odd number for every choice. It's a little time consuming, so make sure you check the clock before you attempt a long-winded method like that on a problem like this. And strive over time to be able to work a problem like this simply thinking about the odds and evens without Okay, how did you fare on this one? Another problem where there are multiple paths to the solution. One of them a little slower, one of them a little faster. Of the two that I'm going to discuss, I think there's probably 3 or 4 different ways to get there. We'll focus on 2. The first one is to represent, and this is great just for practicing your fundamentals of recognizing a consecutive series. So to represent 5 consecutive integers is to say x, or n, x plus 1, x plus 2, x plus 3, x plus 4. And if we do so in this case, we know that we have these 5 consecutive integers, and then we can sort of combine the x's and combine the numbers, and we have this nice snappy 5x plus 10. And we know that 5x plus 10 is equal to 180. So one path to the solution is then to solve for x using that equation, and then go back through and use the second half of the series. Several of you probably did that. I'm not going to demonstrate that solution, though it's entirely possible to work the problem that way. The other half of the series would be represented as x plus 5, x plus 6, x plus 7, x plus 8, and x plus 9. We could consolidate everything here and arrive at 5x plus 35. Now, without going back to use the original number, 5x plus 10 is equal to 180, solve for x, plug back in for x, and work that out, we can simply see that there's a difference of 25 between the two series, 5x plus 10 versus 5x plus 35. Therefore, the value of this second series is simply the value of the first series, which is already known, 180, plus 25, yielding us a solution of 205. Some of you may have done this extremely fast and simply recognize that in a second series of 5, each of these is going to be 5 greater, and that's why I've written them on the board in this way, that there's a difference of 5 right here, a difference of 5 right here, a difference of 5, so forth and so on, for a total of 25. So you can simply add 25 to the first series to calculate the value of the second series. Another way to do this is by using means. And of course, means and medians are equal in evenly spaced series. So when we know we have an evenly spaced series like consecutive numbers, another way to do the problem is to simply take 180 and divide it by 5. This gives us the mean, and in consecutive series, the mean is equal to the median. So it also gives us the middle number of the first series of 5 numbers. And that middle number is 36. And then we could simply plot it out. Okay, the first set is 34, 35, 36, 37, and 38. The second set must continue 39, 40, 41, 42, and 43. And then from there, we could simply type these numbers in the calculator very quickly and arrive at the solution of 205. tough problem here. And it's the reason that you go so fast on all the other opportunities on the test when you can is so that you have the extra time to dig into a problem that's within your range when you need to. So if you feel like you're on the hunt for a solution here, go ahead and pause the recording and give yourself up to 30 additional seconds to solve it, assuming that you saved that 30 seconds by going faster on earlier problems. Now, this is one where I think the simplest, most straightforward way to the solution, as we've seen a couple of times tonight, is just to kind of take it step by step. I do not recommend attempting to type all of this into your calculator. That would be very error-prone and time-consuming. Possible, but error-prone and time-consuming. What I would do here is simply compare term by term. So rather than trying to calculate all of quantity A and compare it to the quantity B, let's just go term by term, and maybe we can get a feel for which one's going to be larger in the end. And what that would look like is, well, clearly the first term is simply going to be 5 in column A. And for the second term, we're going to have 3 times the first multiple of 2, which gives us 6. So the second one is bigger. With the second term, we're going to have 10 on the left, and we're going to have 3 times 4, the second multiple of 2 on the right, which is, again, bigger. For the third term, we're going to have 15, and then we're going to have 18 on the right. You might see a pattern here. And you could count on that pattern continuing. So as it so happens, each term that corresponds to the other first term or second term or third term in the series is going to be larger for the series on the right. Therefore, quantity B is ultimately going to be larger. Once we extrapolate this and do it 20 times, the pattern's never going to change. The pattern on the right will stay consistent. Each term on the right will always be larger than its corresponding term on the left. We can confidently answer B. Moving along, let's try a couple of number line questions here. Combined, I'll give you 2 minutes for these. Now, the first thing to recognize on a problem like this or problems like this is that the GRE never expects you to eyeball the actual value of any of these variables on the number line. The point is only for relative comparison. So what do you know about P? P is a negative number, and it's smaller than -1. S is a positive number, larger than 1. Q is a negative fraction between 0 and -1. R is a positive fraction between 0 and 1. This is the sum total of what you know. So in the first problem, I think it might be easier to actually look at column B first. If we take a fraction and we square it, as we've seen already earlier in class today, that's going to yield a smaller number than the original, but it's still going to be positive here. So for column B, we have an albeit smaller than the original, but still positive fraction. With quantity A, we have a negative fraction on the bottom, and we are squaring it. So when we square a negative fraction, the negative drops. We do get a smaller fraction, yes, but the values here are really unimportant to us. We square a negative fraction, we get a positive fraction. And when you take the reciprocal of a positive fraction, you get a positive integer, which means that quantity A must be larger than quantity B, because the reciprocal 1 over a positive fraction just means you flip that fraction over. Whether Q is 1/2, for example, well, Q squared is going to be a 4th. Flip that over, you've got 4 on this side, positive integer, but you'll always have a positive fraction less than 1 in column B. For the second problem, a little more challenging perhaps because of the subtraction element involved. Let's look at it. If we have a positive integer s and we are subtracting a negative integer p, we're going to be adding an integer. So we have an integer, and let's just assume that they're integers. They don't have to be, of course. It would just be easier for us if we used integers here. So we have a positive integer plus another integer. So this is going to yield a positive result no matter what. And what are the characteristics? Do we know anything else about it? We don't know whether it's going to be an integer or not. We do know that since p has to be less than -1 and s has to be greater than 1, that whatever this total is, it's going to be greater than +2, no matter what. It actually doesn't have to be an integer. This is incorrect. I just think it's smart to think of it as being an integer. So does everyone see that? Hopefully. That if we take a positive number and we subtract a negative number, we're adding them together, we're going to end up with a result that's greater than 2, because we know s is greater than 1, and p, dropping the negatives, is also greater than 1. So we're going to have a positive number greater than 2. For quantity b, we have a fraction, and we're subtracting a negative fraction. So in other words, we have a fraction, and then we're adding another fraction. And both of these fractions are less than 1. So if we take two fractions less than 1 and add them together, we will never reach the threshold of 2, no matter what. This quantity can never be equal or greater than 2. Therefore, column A must be larger. You could think of it this way. Let's say R was 99/100ths and Q was -99/100ths. Add them together and what do you get? You get 1 and 98/100ths. You can't get to 2. You can get close, but you can never get there. And S and P will always be larger than 2, even if only barely. Okay, one final problem for the day. I'll give you 1 minute. Okay, so looking at this final problem for today, hopefully you didn't fall for the trap that the test writers have set for you here. You can demonstrate this with a quick drawing of the number line they have in mind. Most people, well, I shouldn't say most people, what they are hoping you will do is under time pressure, assume that A, B, and C go in that order from left to right. In which case, if they did, then the distance from A to B is 6, distance from B to C is 8, the distance from A to C is clearly 14, and column A would be bigger. However, if you're following process of elimination here, you could simply eliminate B and C, and what happens is you could also have C to the left of A, for example, in which case the distance from C to A would only be 2, while the distance from A to B is 6, and the distance from B to C is still 8, in which case quantity B would be bigger. Now eliminating A, and our answer would be D. Hopefully you didn't fall for that one. If they just give you some random points and tell you they're on a number line, they can be in any possible order you could arrange them in. Okay, guys, thank you very much for sticking around for the number properties lecture today. You're coming very close to wrapping up your GRE course. Please get your homework in order and get ready for session 9. We'll see you then.